Again, good morning and welcome to Physical Science 1. Today is April 6th. We are preparing actually for the second exam. The second exam is going to be immediately after the spring break. So you will guys have a review immediately after the spring break because there will be no live classes after the spring break, at least the first week, okay? Because of the fact that they will be on campus. So the Tuesday before, the Tuesday after spring break. Let me check the date in here to make sure I give you the correct dates. Obviously, I need to follow up with this one with an email. The 20th is going to be the exam review when it's going to be basically made available for you guys. So you'll have the 19th, the 20th, and the 21st to complete the exam review. That's immediately after spring break. And then the 22nd, which is the Thursday, is when you're going to actually have your second exam. Again, I will not be basically holding live classes on those 2 days, namely the 20th and the 20th and the 22nd, but we will resume our live sessions, okay, on the 27th, okay, because next week is spring break, and the week after is the midterms week. So that is basically what's going on. Does this make sense to you guys? So, and then in terms of the content, I still honestly did not, very good. I did not really decide yet 100% on the chapters, all of them together, put together, but you will have more clarifications basically before spring break, actually in terms of the review and what to prepare for. And there will be a lot of questions. You will need to complete it on the 21st. That's a Wednesday. Please, if you have issues with the internet, do not leave it to the 20th or the 21st and then start being alarmed and saying, oh, I don't have time. Can you open it for me? So again, you will have ample amount of time to figure out. If there is a problem with the internet where you are, you need to go to a place where you can, when you can take care of that. And then the other thing also, the exam is similar to the last time when we had it on Thursday. So it's going to be also on Thursday. It's going to open up from 8 o'clock in the morning. I think my first exam on that day starts like 9:30 on that day. So I will be available for you guys if you have questions. And I will not be available for the last hour and a half before the exam is over, which is going to be in the evening. Because then if there is an issue, it's too late for anybody else to basically recover from it. So basically you have to live with it. So that is the only thing. So please start soon on these things. And if you discover an issue, communicate it so that you benefit from it and the other people also benefit from it. And otherwise, basically, that's the thing that happens with the online instruction that we can't really control. So this is basically of what's coming. Today, we're doing chapter 14. There will be an activity associated with it where you're going to do a simple, basically, chemical reaction at home with stuff that you should have access to at home. And if you can't, it's not really expensive to get. So we're going to do basically a simple one. And then we're going to have actually an assignment for for compound naming, which is important. And then, so that is basically for this week. And then next week is your spring break. So I want you also to enjoy at least part of it. I know some of you are working, and so am I actually getting stuff ready for you guys and other classes. Anyway, so let me share with you the screen. It's chapter 14. Let me move this out of the way. Oh man, why did you go all the way down? Okay, good. I'm having issues with my screens in here. Anyway, so we're going to go through basically an introduction to chemistry. So this is not full chemistry. We're going to get elements of chemistry, basically an introduction on a few things. And the role of chemistry in science in general, it plays a major role in science, especially as it's related to biology and geology and even astronomy and other fields. And its interconnection with physics, because physics and chemistry, they're actually, in a sense, chemists are really physicists, no more. I mean, they specialize in one specific area of physics, and that's what chemistry is, really, okay? And then the difference between physical and chemical properties is kind of on one side of the story, on one extreme of the story, is basically the different changes in the physical structure, in the physical properties, basically color, density, and things like that in the material. And the phases, the different phases also, whether it's a solid, liquid, and gas, those are the so-called physical properties. For example, you take the case of water, it's the same chemical formula, H2O, but it could exist in 3 different phases. It could exist in solid, it could exist in liquid, it could exist also in gas, depending on the temperature. So these are physical transformations because the underlying structure of the molecule itself is still 2 hydrogen, basically, atoms combined with an oxygen atom to form the water molecule. These are 2 different things. You start with a gas, super light gas, namely hydrogen, and start with another gas also, oxygen, and you end up with, at room temperature, with a different material completely that has complete different properties. It's a liquid, actually, it's water. So this is actually a chemical transformation. So you go from a gas to a gas with specific physical properties and chemical properties too, to a new compound, which is H2O in this case, that has different properties, physical and chemical too. So in this case, this is actually chemical transformation, where you have 2 different elements combining to make a new one, or the opposite also is true, okay? So this is basically in a nutshell what we're going to be talking about. Then elements versus compounds. And elements, like for example, in the case of helium, iron, gold, silver, oxygen, nitrogen, all of these are elements, okay? Obviously, they can combine and form compounds. For example, a nitrogen atom and a nitrogen atom, they combine and give you the molecule of nitrogen, which is the main component in the air. So in this case, you have a compound, although it's made up of similar elements. For example, the case of water, H2O, you have, again, 2 different elements, and they come up with different proportions. You have 2 of one element, namely hydrogen, and 1 of a different element, namely oxygen, combining and giving you a compound, in this case, which is water, okay? So again, this is how we're going to, this is basically the basic ideas that are coming from this introduction. And how to name compounds, which is a very important concept that we're going to do at the end of the day. Again, chemistry is the study of matter and the transformation it can undergo. Historically, it started with in the Middle East, at least before that, way before that, where the transformation of materials was studied, and in the Middle East, the word alchemy, okay, was basically concerned with trying to get some sort of a transformation so that you can end up with gold if you combine enough metals together, or do some transformations together so that you can get some precious metals. It turns out to be not a chemical process to do that. We will learn about it down the road. It's actually a nuclear process where you can actually get gold out of a different element. But it's still, this is basically how what the purpose of it in here is. So the key word in here is transformation. Okay. Again, these are some different kinds of metals. Probably this is diamond. Okay. Chemistry plays a role in all branches of science. Think about astronomy. I mean, yeah, I mean, you're thinking probably in terms of the material used to go there and use it to protect the astronomers themselves, and the different materials that makes up that. That is actually, yes, chemistry, you're right, and metallurgy probably too, and other fields of science, material science, that is, okay? But look at the different structure of different elements in the astronomy. For example, the moon, its composition, and what it tells us about its evolution, its history. And this is true not just for the case of the moon, but it's true for all case of planets that we study. So chemistry plays a major role in astronomy. Without it, we will have very little understanding of what's going on in there. So chemistry plays a major role in science in general, and especially its connection with biology, for example, and especially in the terms of the organic chemistry, that component to it. In terms of earth science, how Earth is basically, geology is shaped with the different interactions of different compounds, different basically elements, and changing from one form to the other, whether in the atmosphere or also in the crust, or even inside the core of the planet. So this is an example of that, how chemistry helps us understand these different processes involving also different parameters such as heat and other forces in nature. Okay. Astronomy, as I was talking about, the fact that it is connected to it in trying to understanding, for example, the chemistry of different planets, different actually stars, and different composition of compounds everywhere else. You look, for example, to a star or a galaxy, impossible to reach with current technology, period, end of the story. We have never been outside of our solar system, as a matter of fact. We have not even landed anywhere else other than a few places like Mars, for example, the moon. We landed also for a brief moment on Venus for probably about less than, I don't remember the exact number, but it's less than an hour for sure. We landed for also about 90 minutes on the moon on near Saturn, and that's it. But other than that, we use spectroscopy to understand the composition of this different objects and the objects that are far away. Spectroscopy tells us a lot about the structure of the different elements. You look at, for example, an article in astronomy, or you read about it, or you watch something about it, and they will tell you this star have this much oxygen, this much hydrogen in it, and this much helium in it, and it has traces of this element and that element. How do they know that? Since we have never been outside of our solar system. Again, we use chemical analysis, usually using spectroscopy, to study the different components of those objects. Okay, its connection or interconnection with physics is very, very close connection. It's the mechanics of the motion of the electrons inside the different elements that help us, first of all, understand that. And that's a mechanical motion, and that's a physical interaction between the charges, and that is a physical interaction between the different charges, for example, to form the H2O. So again, there is a connection between these two branches of science. And as I was saying, chemists are actually specialized physicists no more. Okay, chemists are really physicists in their core, except they specialize in a specific area of physics, and then actually they branch out of it, namely the fact that they are concerned more of the rules of how this transformation are happening, and how to make new compounds out of old ones, and how to come up with different materials that require different requirements, for example, in terms of specific requirements, whether related to namely physical requirements, like, for example, conductivity, whether or not insulation, whether or not in terms of different properties, strength, for example, and different requirements, and weight, for example, or lightness, if you want to take it outside of the Earth. So again, different materials are required in there, and they are not only concerned in astronomy. They actually have applications in engineering, and application in the industry too. Because if you look around yourself right now, where you're seated, almost every single thing that you're looking at had chemistry involved in its making. Okay, and that is important. From the food you eat, to the clothes you're wearing, to the pieces that you have to use, to the electronics that you have, to everything else, has at least been treated as somehow or the other by chemical process, or had chemistry involved in its making, basically. So that's why it's important in here. So it's an important subject. Again, obviously, its connection to material science is a big deal. Okay, and that is where the applications is. Actually, material science is a kind of a bridge between physics and chemistry, because that's where. And if you ask a material scientist, he will tell you that I am neither. Okay, I'm just doing material science. I want to get some material that requires some physical and chemical properties that I have to end up with. Okay, they are very highly specialized fields in this case. Most of the materials items in any modern house are shaped by some human devised chemical process somehow. If you look around in your kitchen, as I was saying in here, almost everything that you're looking at, from the energy that powered this light bulb, which is a chemical energy, okay, converting fuel basically into some sort of with a generator, of course, to the paint in here, to the different materials in here, to the glass in here, to the different coffee in here that you have, to the material that make up this refrigerator, what is inside the refrigerator, to the different materials in here, to this burning of the flames in here, to the material that makes them, to the material that went into the production of this food, to everything else in here that you're looking at has at least some sort of a chemical process involved in its making, okay? So that is basically what this is. That's why it plays a very important role in life. Okay, again, in biology in here, if you open the refrigerator, you will find a lot of medicine, and medicine actually has is made using chemical processes, okay? Now we're enjoying, at least to some extent, some success with this fight against the coronavirus, is due to a great deal to chemists and biologists working together and coming up with different, basically, vaccines. So that is good, actually. That is good. So it's an important. It plays a. Imagine if we did not have chemists around. What would have happened to us without for this coronavirus? I mean, the biologists, they will be working on their own, but they have no clue how to basically take the next step and make it available for the general public, like you and I. Okay? You guys agree? It's very important. Yes, no, maybe? Okay, very good. So, let me share the screen again. So again, I talked about all of these things in here. Of course, there is, I mean, it is also heavily involved in terms of the decision making. Like, for example, I was just talking about the coronavirus and how that basically process went all the way to the government and through the process of allocating funds for it, and also through, so it is important, and it's through all of the steps for it too. So here is an example: collagen, which is a cross-link inhibitors that significantly reverse various aspects of aging, have recently been discovered. So basically that story of the old men getting younger, so it's probably possible in here, is it? So they are clinically tested to be safe, to be safe, available to the general public. Please do not read this one as being true, okay? But the thing with it is, so it's an evolution of the process, okay? So there is some serious research in this field, okay? Available to those who are, so at this point, prohibited because growing old should be natural, okay? At this point, it's a debate. There is political debate always involved, different kinds of decisions, including the virus itself. Unfortunately, including the virus itself, it should help, because that should really probably, at least in my opinion, should be a public safety number one. So if that is the case, then everybody should be vaccinated. So there is, at least when politics involved, you have all kinds of other things that are involved in here. Okay. Here is the deal about the sub-microscopic, basically, universe. At that point, there is a lot of them. They're so tiny and small, and there is a huge number of them, okay? Typically, on 1 mole, for example, of something, which is its mass of that, for example, if you have, 4 grams of helium, that's an example, you have an Avogadro number of those particles, 10 to the power 23. It's a huge number. I mean, it's 1 followed by this many zeros. And for example, if you take a grain of sand, 1 grain of sand has roughly about 125 million billion trillions of atoms. That's 1 grain, not the whole mole, of course. The whole mole will have far more than that, okay? So that's a huge number. So if you want to imagine that, and if you want to bring it in terms of grains of sand, 1 piece at a time, trying to see how many that will amount to. So you say, okay, I want to make a model of a grain of sand out of grains of sand. So in other words, you have a grain of sand, it has this many atoms in it, okay? So what you say in this case, assuming the atom is the size of a grain of sand, which is tiny, okay, which is very tiny. I'm going to make a model out of it in here. I don't want to break this one. Very tiny, okay, that's a grain of sand roughly, okay. Now you take that and you bring another one. So you have two atoms now, and you bring a third one, and you bring a third one. How much grains of sand are you going to accumulate? You're going to have, of course, this dune in here, but that's not enough. That's not that many. You have to have about 250,000 of this, which is far more than what you're going to have in the desert, the Sahara Desert, which is the greatest desert in the world. So probably all the deserts combined, they will not have enough grains of sand for you to make up how many atoms inside a grain of sand. Just to tell you how small these things are. The atoms are very, very, very small, okay? The atoms are extremely tiny, okay? So if you take a meter, this much meter, no, actually slightly more, it doesn't matter. This is roughly about a meter. And you divide by 10, so this is 10 centimeter, okay? And you divide that by 10, this is about 1 centimeter, okay? And you divide that by 10, so this is roughly about a millimeter separation, or less actually than that, 7 millimeter. Take that millimeter and divide it by 1,000. So you're looking for a size that is extremely smaller, and you still are a micrometer. You take that micrometer, which is 1,000th of the separation, and you divide it by another 1,000 to get into the nanometer. And even then, you are not in the size of the atom. You have to go even 1/10 of that. So it's 1/10 of a billionth of a meter. That's the size of the atom, super small, okay? Or 1/10 the millionth of a hair, okay? You take that piece of hair, the width of it, not the length, the width of it, and divide it into 1,000,000 pieces. And that piece that you have left from it, divided into 10 to find the size of the atom. So it's super small, okay? Super, super, super small, okay? And that's why we cannot see them, because our eyes are sensitive actually to light. And the wavelength of light is about 7,000 times bigger. That is at least the shortest wavelength that we can see. The shortest wavelength, which is the blue light, is about 1,000 times longer, bigger in size than the atom. So if the atom was this size, the light is about a kilometer away. That's a huge thing. That's why we cannot see them, because the light is not small enough to discern them. So even if you take the most powerful telescope and use a magnifier, with a magnifier, you're not going to have an image of the atom, because after all, that light is not going to resolve the different atoms, because they will be too close from one another. You cannot see them. The light is too long there for them. We took pictures of the atom, but we didn't take it with light, because light is too long for them. We used actually an electron microscope, and the electron behaves like a wave on that scale, so that its wavelength is of the same size of the atom. So that's why we were able to take pictures. Fuzzy, albeit not exactly perfect resolution of it, but it's still, we had a picture of it, but not with a regular EM microscope, the one that we use for our visual sight. Why? Because the wavelength is too big for light. Even the shortest wavelength that you can think of, which is the violet actually, or the blue side, is 1,000 times longer than the size of the atom. So it's a very tiny thing. That is the atom, okay? So are atoms made out of molecules? Or that's really the other way around, okay? So molecules are made up of atoms. So if you look, for example, at the water, as I said the example earlier, it's made up of two different kinds of atoms. It's made up of a hydrogen atom and an oxygen atom. And this is the ratio with which they are made. In this case, you have 2 hydrogen atoms and 1 oxygen atom. So that is the ratio with which you make this ones. Again, physical properties has to do with the look of the object, or actually its physical properties, namely how strong it is in terms of physical properties. So in this case, the gold is opaque, meaning you cannot see through it. Okay, it's not transparent, it's opaque. It has this color, which means that it's reflecting the yellow color. And at room temperature, which is 25 degrees Celsius, it's solid, okay? And its density is 19 grams per cubic centimeter, or 19 grams per milliliter, which is the same thing, okay? Diamond, as opposed to gold, is transparent, not opaque. You can see through it. Diamond has no color. That's because it's transparent, basically. You can see through it. Diamond in room temperature also is solid. The density is a lot less than that of gold. Gold is very, very, very dense metal. However, there is another property. If you take, for example, gold and you scratch it against a metal, it scratches easily. If you take, for example, diamond and you scratch it against metal, it scratches everything. So a diamond actually has a very, very, very strong property in there, and that's why it's used actually for digging, for the wells for oil, for example. They use diamond actually for those metals in there because it can break through the rock easier than anything else. Okay. Then if you try to do it with gold, gold is actually very useless when it comes to that. Okay. And water, on the other hand, at room temperature, it has a different physical property, which is liquid. At room temperature, it's also colorless, similar to this diamond. It's transparent. That's the same thing as saying colorless. And its density is an easy number to remember, which is 1 gram per cubic centimeter, or 1 gram per liter. So in this case, if I take this diamond and put it in the water, it's going to sink. And if I take this gold and put it in the water, both of them are going to sink because their densities are larger than that of the water. So these are physical properties. Now, chemical properties, though, they describe a substance to transform into a new substance. Okay, here is an example. You have an example in here, which is iron has been exposed to the elements, and it's going to react with the oxygen and form different kind of iron oxides. And that is what you look at. So that is actually a chemical reaction in this case that transforms the iron into different compounds. Now, the color of the iron and the color of the oxide are not the same. So the physical properties also change in their chemical transformations. So when an object goes through a chemical transformation, not only its chemical properties change, but also to do its physical properties. Whereas the other way around is not true. I mean, a substance can go through physical transformation. For example, the case of water is a typical example that can change from solid to liquid, but its chemical properties stay the same. Both of them are still H2O, okay? Still the same compound. So here you have a physical transformation, still H2O for the water, it did not change at all. And here it's in one phase liquid, and in here it's in another phase solid. And the same thing is true in here for the case of mercury. Mercury has a different basically density depending also on the temperature. This is 25 degrees and this is 100 degrees Celsius. So again, it's different properties, okay? Obviously it went through a phase transformation and now it's being evaporated. Actually the water is the one that is evaporated. But it expands in here, and that's what you read in terms of the temperature. So you could use it actually for a thermometer. So again, it's a physical property in here. These ones are actually chemical properties, and this is what I want you to do today at home. And I want you to take pictures of it, and I want you to also describe the reaction in there. So the first one is methane. Do not do that, okay? Even if you have access to it, we really don't care about it. I really don't want fire in there, okay? So methane in this case reacts with oxygen to form carbon dioxide and water. Baking soda, that's what I want you to do. Go and grab about a teaspoon of baking soda You should have access to it at home because most of the time this is a household item. If you don't have it, it's not expensive to get, okay? And then vinegar also, which is accessible, should be. And you can use any type of vinegar. It doesn't have to be a white vinegar. It can be any kind that you have access to. Combine the two, take a picture of it, okay, and describe what happened, okay, and try to feel it. When you do feel it, please wash your hands afterwards, okay? That's the only requirement. So this is also another chemical process that involves the carbon dioxide and water, how they form this one on the different materials in here, okay? So these are chemical transformations. So the material itself has changed. You used to have methane before and oxygen. Now you have new materials in here. You have carbon dioxide and actually water. Same thing in this other two examples in there. Is everybody clear on the assignment today?
You want us to show baking soda and vinegar, or just pictures of both of them?
No, I want you to do the chemical reaction. I want you to actually take about a teaspoon of baking soda and a similar amount of vinegar, and mix them inside a hopefully clear container, so that you can see through what's going on, and describe what happened and take a picture of that.
So take a picture of the end result and describe
Yes.
what happened. Okay, thank you.
Yeah. Okay, very good. Unfortunately, if we were in the lab, we would have far more fun with these things than this one, but we're not. I mean, even if we are in the classroom, we usually bring the demos for a lot of our chemical reactions in there. Okay, but this is the closest you're going to do, at least with hands-on stuff from home, okay? And I really don't want to I want you to be safe too. That's why this is a safe bet, okay? Because when you're dealing with chemistry, you have to be very, very careful. You have to really be cautious with what might happen, okay? I remember one of the chemical reactions I did in high school was involving basically dissociation of the hydrogen, the water into hydrogen and oxygen, and the byproduct was supposed to be hydrogen, and hydrogen is very reactive to oxygen, and we were very careful with it when we recombined it back with the hydrogen, basically through a chemical reaction. Basically, all you have to do is ignite it again, and it's going to have an explosion, and that explosion will lead to water again. Okay, so that was the proof basically through that. So you have to be very careful, and that was a high school chemistry, let alone in college. So the substance is identified not only by the kind of atoms it contains, but also by those atoms and how they are connected. Okay, so you cannot tell me you have this many things. So how are they bound? That is actually very important. So during a chemical change, a new substance is formed as atoms rearrange themselves. Here is the process, more or less. So you have methane, which is a carbon atom connected to 4 oxygen atoms, okay? I'm sorry, 4 hydrogen atoms. Okay, the blue ones are the hydrogen atoms. And you bring the oxygen in here. And usually you would want to ignite the reaction. Once it ignites, you can start it, okay? So you need somehow to facilitate it, to help it through. Because if you put, if you let go of methane inside the room without getting a facilitator, without getting a catalyst for it, it's not going to happen. So you need at least a little bit of energy. Once it starts, then it's going to be self-sustained. So now the bonding between the different elements is broken because of that heat. That is the initial heat, okay, added. And now you have loose structure in here. If you count how many hydrogen atoms you have 1, 2, 3, and 4. You count in here, you have 1, 2, 3, and 4. So you didn't lose a single hydrogen atom. You count how many oxygen atoms you have. We have 1, 2, 3, and 4. You count in here, there are 4 of them. You count how many carbon atoms you have in here, and you still have 1. So basically, it's the same elements as you started with. Now, they want to rearrange. Once they do, 2 hydrogen atoms are trapped by the oxygen, and they form water, this water. 2 hydrogen atoms, they're trapped by this oxygen, and they form the second water, okay? Now you're left with this oxygen and this oxygen. They are free. and they combine with the carbon, and they form carbon dioxide, and the other one forms water. So it's the same elements you started with is the same elements you end up with, plus a release of more energy, by the way. So yes, you need an energy to break these bonds, and that's true. Once they are broken, they will reassemble and give you more energy, and that's why that chemical reaction is actually useful. Okay, that's why you could cook your food with it. So it's useful because the net energy output is more than the net energy input. This kind of reaction is called an exothermic reaction because it releases more heat than it takes, okay? So the net heat, you'll have a positive heat out of it, versus other kind of chemical reactions that require actually more heat than what they give you. Those are called endothermic reactions. For the case of the chemical reaction that you're going to do, that's part of the process you're going to describe, did it require for you to heat it, or did it happen by itself? Okay, it would be nice if you can get your hand close from it. Obviously, if you take the baking soda from the refrigerator, and if you take the vinegar from the kitchen, you might feel cold from it, and you might not feel temperature. So try to feel it to see if you're going to get heat out of it or not. Okay, there is definitely energy in those popping bubbles that are going to come out of it. Okay. But is that enough for you to cook your food with having that chemical reaction, mixing baking soda with vinegar? Probably not. But with methane combining with oxygen, that is actually a very highly energetic reaction. It releases a lot of energy, okay? But you're not supposed to do this at home. This is not one of the things we're going to be doing at home, okay? Is this clear to everybody? Yes? Yeah, I don't want you guys to play with fire because you might cause damage to something. Then I really don't want you guys to do that. And if we were in a lab and controlled setting, probably we could. We would, but not here, okay? So again, you get carbon dioxide and water, and this is a typical reaction. In this case, this is called the combustion. This is basically what you end up with, okay? So if you count the atoms, the starting is the same as the ending. You didn't add more atoms or you lose atoms. And this is the basic for how you balance chemical reactions. You balance chemical reactions by counting how many elements went in, and it must match how many elements you end up with. And you keep on trying different numbers until you find the proper ratios. And those means that that chemical reaction would be balanced. This one is balanced as is, because I brought two different oxygen molecules, combined them with a methane molecule. I ended up with two different water molecules and one carbon dioxide molecule, okay? So this chemical reaction is balanced. It would not be balanced if I just brought one of this and one of that, and then ended up with one of this and one of that, because then it's clearly I have a problem. Because if I ignore one of this, where's my pen in here? If I ignore one of this, for example, this is not there, and this is not there in the counting, and start counting how many reds I have, 1, 2, and I end up with 1, 2, and 3. I know that my chemical reaction is not balanced because I have more oxygen atoms than when I started with. I have 2 to start with, but somehow I ended up with 3. Same thing in here. If I count the carbon, the hydrogen atoms, there is 1, 2, 3, and 4. And in here, if I count them as 1 and 2, remember this one I did not include it. Okay. Then in this case, I know the chemical reaction is not balanced. But if I bring 2 of this, not just 1, and I end up with 2 of this, and then start counting, my chemical reaction is balanced. So this is the essence of what the chemists do, at least in chemistry classes. They usually are concerned with equations being properly balanced, in addition to the fact that they have to balance the energy also, because they have to fully account for the energy, where it went and where it's coming from, and so on and so forth. Here's another example of a chemical reaction. You bring 3 different molecules of oxygen, and you end up with 2 different molecules of ozone, which is O3, okay? So again, in this case, you will require the energy to break these bonds and the energy that is released from this formation of these bonds, okay? So this is a chemical transformation. Although you start with an oxygen and you still have the oxygen, but in this case, it's still you still have basically the structure has been rearranged in this case, okay? So a chemical change forms a new material with its own unique new set of physical properties. Case in point, for example, this chemical reaction, I forgot to mention that, but this is actually a gas. This is also gas, and this is also gas, and this is liquid at room temperature, okay? So now you start with some physical properties and you end up with different physical properties. In this case, you start with gas and you end up with gas, so it's fine. So both chemical and physical changes result in physical appearance changing, namely physical properties changes. We have quite a few slides, so we probably need. Okay, tarnishing a piece of silver is actually a chemical process, a chemical change, because actually you form silver sulfides in here. That's why you do this one. So it's a chemical reaction. So again, this is typical stuff. I know we're doing an introduction to chemical elements of chemistry. So this is an introduction. So hopefully this will be, we will have more materials down the road on chemistry, okay? So elements, a material made up of only single, so that's we saw last time, and we said that an element and the atom are sometimes used interchangeably. Pure gold is, for example, an example of an element. Atoms, the fundamental unit of an element, okay? So this is basically some basic definitions. So the elements usually are for macroscopic properties, like for example, gold. And usually the atom in here is used for sub-microscopic properties. Here's an example of compounds. I have the oxygen gas, which is O2. I have the ozone, which is also another type of oxygen gas, which is O3, and have the sulfur, which appears in S8. So in this case, the element is still oxygen, oxygen, sulfur, and gold. But in this case, this is a pure element, whereas the others are compounds, okay? In this case, if you can think of this gold as being a compound of just a single element. Usually, compounds are made up of different elements in them. Case in point, for example, this one. This is sodium chloride, which is NaCl, which is regular salt, everyday salt, okay? And this is ammonia, which is you have 3 hydrogen atoms combined with nitrogen forming ammonia. So again, this is another compound, okay? Typically, they are of different elements. Compounds have properties uniquely different from the elements that you start with. Case in point, for example, you have in here sodium, which is this type of metal, which has physical properties in terms of its ductile properties, it's in terms of tensile properties, in terms of its resistance to tension, it's basically all kinds of physical properties. And in terms of its also chemical reaction and so on and so forth with oxygen, which is highly basically reactive with oxygen. It's a very dangerous element actually to have around free, not in the, and then chlorine, which is actually a gas, okay, which is also a very dangerous element and highly reactive too, okay. This is an alkali. If you look at the periodic table, it sits right on the top in here on the first. This is the other one, the chlorine is actually a halogen, sits actually on the next table to in the periodic table. You combine the two through a chemical reaction, you end up with salt, which has different physical properties and chemical properties altogether than the other two, okay? A chemical formula is used to show the proportions of which elements combine to which. Case in point, for example, we have seen this one already, NH3, H2O, O3. Those are basically different kinds of chemical formulas, sometimes referred to simply as formula. Here is more examples. sodium chloride, NaCl, and those are the chemical formula or the formula for them. How do you name this element? So what you do in this case, you start with the farthest element in the periodic table on the left. Sodium sits in here to the left, chlorine sits in here to the side, in this side. So you start with this one first, with sodium. So you say sodium, and then add ide to the element to the far right. So in this case, I have chlorine on this side. So I add I to it and it becomes sodium chloride. So that's how you name stuff in here. So you look at the periodic table, which one sits to the left, that's what you start with. And then you look at the element that is on the other side and you add I to it, say oxide. So basically that is how you call elements in here, or in this case, chloride or fluoride, okay? So in this case, this is the example, sodium chloride. Here is the one to the left is sodium, the one to the right is chlorine. So we're going to start with the element to the left, that is sodium, and then you add I to the other one, and that is how you end up with sodium chloride. It's just in depth in here. This is how the element sodium chloride is named. So that's 2 rules so far, okay? With different possible combinations, sometimes you have more than a single possibility. You have, for example, CO and CO2. Both of them, combination of carbon and oxygen. But in here, you have a single oxygen, and here you have 2 oxygens in it. So this one is called carbon because it sits to the left of the oxygen. And in this case, you have oxygen, which is oxide. And in here also it's carbon. And in here also it's an oxide, but it's differently, clearly they're not the same. This one you add to it the prefix mono. And this one you add to it dioxide. So this becomes carbon dioxide and this becomes carbon monoxide, because just to make the distinction between the two. Okay? So here is the prefixes. You have the mono, the di, the tri, and the tetra. In this order, 1, 2, 3, and 4. Okay? That's the example I was talking about. Carbon monoxide, because you only have 1 oxygen, and carbon dioxide, because you have 2 of them. Okay? Here is another example. You have 2 hydrogen in here, and you have 2 hydrogen in here. You have 1 oxygen in here, and you have another 2 oxygens in here. So this is actually a dihydrogen. You start with hydrogen because it's on the left, and the oxygen is on the right. So it's a dihydrogen monoxide, because you only have a single oxygen in here. This one is a dihydrogen dioxide. This is every day is called water. This is actually called, what is it? Hydrogen peroxide. So you can use those alternative names, the known names, but this is the proper way of naming them. Okay? At least the chemical way of this to name them. Obviously, you have to be careful with this too, because this one you can drink, this one you can't. Okay? This is not actually advisable to drink. Actually, it's toxic. This is used actually as an alternative for people who are sensitive to alcohol, like myself, to use it for basically cleaning wounds and things like that. Okay. So again, the common names for this one is hydrogen, instead of saying dihydrogen monoxide, and instead of saying dihydrogen dioxide, you can call it hydrogen peroxide. That's the common name for it. That's what you see actually in the box labeled on it. So again, here are the rules. First, start with the element furthest to the left in the periodic table. For the elements to the right, add the suffix "ide." With a different possible combination of elements, use the prefixes to remove ambiguity. Okay? Common names are sometimes used for convenience, like, for example, case of water. Here is an example. What is the name of this compound? Okay, that's not true. Chlorofro, I don't know what that is. C-bur-4, that is not how the proper name for it. Carbon bromide, it's close enough, but I have 4 of them in here. So it's carbon tetra for 4, bromide. So I start with carbon, And then I go to the second one, which is bromine, add to it ide, so it becomes bromide, but I have 4 of them, so it's carbon tetrabromide. Okay, so I know we finished a little early today. I was thinking actually to combine it with another chapter, but I didn't think that's going to be really useful since we have an activity related to naming compounds, which is really at the end of this section, at the end of this unit. So I want you guys to go through all of those basically exercises and complete them, in addition to doing the, that is actually for grade 2. So that is not an extra activity with the discussion today, where you guys are going to actually do a chemical reaction at home. Hopefully you will have fun with it. And it's fine if it's messy, that's fine, okay? It should not be, because you're going to take just a spoon, a teaspoon of each, and you combine them carefully, and you take a picture while they're reacting, and you describe what's going on, and try to see in terms of the heat, and try to see in terms of the bubbles that form, in terms of everything else, and how you describe it, okay? And then try to have a feel for the results of the compound, okay? You have the reactants, and there is more terminology coming down the road. The reactants in this case are clearly the baking soda and the vinegar, and the products in this case are supposed to be the products from these chemical reactions that are, you can describe their at least physical properties after you touch them, and it smells a little, I know. Okay, so you have to be careful with that too, not to get too close around. But the vinegar is usually a strong compound. Okay, anyway, so I'm gonna stop the recording now, and I will see you guys on Thursday, okay? Same time. Sounds good? Okay, very good, thank you.